So before we do this question, we're going to watch the video of Indiana Jones running away from the big, perfectly round rock, okay, in the greatest Indiana Jones movie ever, The Raiders of the Lost Ark. And you do it right the first time, you get to make lots of sequels. You do it, oh, wait a minute, that rule doesn't apply because you can do it wrong and make lots of sequels to Disney. Anyway, what we're going to do is we're going to look at that, and then we're going to see if we can answer this question from a work energy theorem standpoint. Okay? Okay, so in this question, the large round stone, which is 400 kilograms, nearly runs over Indiana Jones. From a physics perspective, what height would it have had to drop from if it rolls 30 meters through the tunnels, okay, against a frictional force of 800 newtons and was moving at 4.5 meters per second when it sealed shut the temple? Okay, so write that one down. It's very much like the ones we were doing yesterday. We're looking for the height it was dropped from. Think about what it means if you drop something in terms of how fast it's going when you drop it. Okay? And we are talking about the end point being as far down as it can go. And see what you remember from yesterday. So essentially, we've got the same question we had for all the other ones we did. It's essentially an inclined plane. Okay? We've got the rock starting at the top of this tunnel, basically, okay, where its initial velocity is what? 0, right? Starting from rest, okay? And it's going to, it's at a height that we're looking for, okay? We're looking for its initial height. The end of that question is here at the end of the tunnel, okay? Well, here at the end of the tunnel, its final height is 0 meters. And its final speed is 4.5 meters per second. Okay? We know that along the length of the tunnel, which is 30 meters, there is a force of friction of 800 newtons. What is friction going to do to the energy of the rock? It's going to slow it down. It's going to take energy away. Right? You're doing work against friction. Okay? So work then is definitely being done because the energy at the top and the energy at the bottom are going to be different. Okay? So I need to set up work energy theorem. The work done by friction or against friction is going to be responsible for the change in energy of the rock between the top and the bottom. Everybody follow me there? Okay. Now, they tell me the force of friction, and they tell me the distance over which it's going to work. Okay, so I have force times distance there. Okay, and then I'm going to have my mechanical energy final minus my mechanical energy initial. From yesterday, how do we calculate mechanical energy? It's the sum of what two things? Kinetic and potential. Okay, so that means I expand this out. Force times distance equals, okay, EP final plus EK final minus EP initial plus EK initial. Okay, I just wrote 4 different types of energy in there. Are any of them 0? Final potential is 0. Any others? Initial kinetic. Okay, my initial velocity is 0. Okay, did that just simplify that question a great deal? Okay, so now when I expand this out, it's actually going to look a little bit shorter. Okay, I'm going to have force times distance equals 1/2 mvf squared minus mghi. That's all there is. Okay, is initial potential and final kinetic. So can I isolate the initial height? since that's what the question wants. Okay, so if I want to get the initial height, okay, the only trick to this is that this is negative right now. Okay, so what I often do to avoid that is I'll actually add this over to this side. So I'll have mghi plus fd equals 1/2 mvf squared, and then I'll subtract fd over to this side, because I don't like solving for things that are negative, because I always forget that they're negative and then I get the wrong answer. Okay, so what I'm saying here now is my final energy minus the work equals the potential energy. Is that okay? Or equals the initial energy. What do I have to remember about the work? Friction makes you lose energy, so the work will be negative. My force of friction is negative in this question. That's what I have to remember. Okay, so I'm going to go 1/2 times 400 kilograms, the mass of the rock. Whoops, sorry, I got to manipulate first before I get to that point. I just got to hit myself. Okay, I want HI by itself. What do I do with the M and the G? Divide. Okay, now I can plug in my numbers. So HI is going to be 1/2 times 400 times 4.5 squared minus negative 800 newtons times 30 meters divided by 400 times 9.81. I think I got all the right numbers there. Yes. Okay, so now that I've got all those numbers, now I just need to plug them into my calculator. So 0.5 times 400 times 4.5 squared, okay, minus negative 800 times 30. Okay, divided by 400 times 9.81. Okay, so the rock was dropped from 7.1 meters above him, or above the ground actually, okay, which would seem to fit since he turned and went like this and looked almost straight up, okay, when he saw the rock. It was quite far above him when it started. All right, any questions on that one? So, like, in the end, did we have a whole lot of numbers to deal with here, or did we simplify it quite a bit? Okay, on an exam, I probably wouldn't make it much harder than this. Okay, I probably wouldn't have all 4 types be a non-zero value, okay, because that's a lot more manipulating, a lot more algebra. This question tells me if you understand the concept, okay, and I already know you can do the algebra, okay, so that's what I'm concerned with. Here's the one I wanted you to do. Okay, I would like you guys to try that one. It's pretty straightforward since it's frictionless. Okay. Since it's moving at a constant velocity, what kind of energy is changing? Potential. Yeah. Okay, we're only making it go higher up the thing. Do we know how much higher? Since we start at the bottom and we go up 7 meters, okay, the work being done is only changing the potential energy, okay? Final minus initial, and our initial is 0 because we start at the bottom of the ramp, okay? If all I want to do is find the work, it's just the final potential energy. Okay, so M times G times H, take your 80, multiply by 9.81, and then multiply by 7 meters, and you'll get 5,500 newtons, or joules, sorry, not newtons, joules. Okay, everybody all right with that? Okay. Okay, try that one. About the same, but with the other kind of energy. What do you have to do with the 55 kilometers an hour? Make it meters per second, yep.